Yeah, good afternoon. Today is the week 8 of the live interactive session for the course Introduction to Atmospheric and Space Sciences. So last class we were mostly discussing about the different lab stages like dry adiabatic, saturated adiabatic, marsh adiabatic, lab state, etc. So today we will start with discussing a few things, few interesting facts about clouds. Then we will move on to what is fog, and then we will discuss how we can determine the stability of the atmosphere. So today we will start with what are clouds. So clouds, as we know, are formed by tiny droplets of water or ice. So clouds are basically formed by tiny droplets of water or ice. And based on the height of the cloud, it may either contain like water in the form of droplets or in the form of ice. Yeah, so based on the height of the cloud, it may contain liquid water or ice. So if the clouds are formed in very high altitudes, in case of high altitudes, due to the lower temperature, the clouds that form at very high altitudes, where the temperature is very low, water vapor eventually condenses to form ice. Whereas in case of clouds that generally form at low altitudes, clouds generally contain water droplets. So based on the height of the cloud, the composition of the cloud may vary. Either it will contain only ice crystals if it is forming at very high altitudes, or it may contain only water droplets when it is forming at very low altitudes. And now let's see how these clouds are named. Cloud names are nomenclature of clouds. So generally, the name of the clouds are obtained by combining name of cloud's shape plus name of cloud's height. So from the name of the cloud, we can understand what is the shape of the cloud and also at what height generally these clouds are. So it was in 1802, the scientist looked forward invented this cloud naming system that is still in use today. Howard basically used Latin names to describe the clouds. So the first, so as I said, cloud names is basically a combination of cloud height and cloud shape. So the first part of the cloud name describes the height and second part is shape. First part of the cloud name shows its height and the second part of the cloud name shows its shape. So we will first see what are these first parts in cloud names. The prefix that is there in cloud names. The prefixes describing heights, cloud heights. If the clouds are high clouds, which means they are basically present at a height of greater than 20,000 feet or 6,250 meters. So these clouds are generally found in the atmosphere at a height greater than 20,000 feet or 6,250 meters. So these clouds have the prefix cirro, CIRRO. And in case of mid-level clouds, which are basically found at a height of 6,000 to 20,000 feet, or if we express in meters, 1,875 to 6,250 meters. These have the prefix called alto. And third, the low-level clouds, which is generally found at a height of less than 6,000 feet. Feet or less than 1,875 or less than 2 kilometers. It doesn't generally have a. So in case of high clouds, which are basically seen at a height of greater than 20,000 feet or greater than 6,250 meters, approximately 6 kilometers, are basically having a prefix of cirro. And in case of mid-level clouds, which are generally found at a height between 6,000 to 20,000 feet or 2 kilometer to 6 kilometer height, they are basically having a prefix of alto. And low-level clouds, which are at a height of less than 6,000 feet or less than 1,875 meters, generally doesn't have prefix. So high clouds are having the prefix cirro, mid-level clouds are having the prefix alto, whereas low-level clouds doesn't have a prefix. Now based on shape, so this is based on height. Now let's see the second part of the cloud name. So the first part basically shows the height at which the cloud is there, and the second part shows the shape. Second part of the cloud name generally shows the shape. So based on shape, if we divide the cloud into different types, we have cirrus clouds, which are generally curly or fibrous. And then we have stratus clouds, which are generally layered. And then we have cumulus clouds, that is having a lumpy or wild. We can show you some figures. yeah, as you can see, these are cirrus clouds, which are generally like this. They are fibrous or curly fibrous kind of clouds are generally cirrus clouds. So these are some photos of cirrus clouds, curly or fibrous. Now when you go for straightest clouds, straightest clouds look like they are gently layered in structure. Straightest clouds are generally layered in structure. Cirrus clouds are generally uh, curly or fibrous, and if you look at cumulus clouds are like this kind of lumps, um, yeah, lumpy or piled up kind of thing. It will be piling up one above the other, or it will be like lumpy, very much lumpy kind of structure. So that is cumulus. Individual clouds itself are kind of very big in case of cumulus, whereas cirrus and stratus was kind of layered or kind of very thin clouds. So that are the three types of um, clouds based on shape. So we have cirrus, stratus, and cumulus. So those are three types based on the shape of the cloud. Now there is another type of cloud. It is called nimbo or nimbus. So this is also a prefix which is added to cloud. This is a prefix which is added to cloud names to show that the cloud can produce precipitation. So basically, if a cloud is capable of, so if a cloud is basically rain bearing, generally rain bearing clouds will have a prefix of nimbo or nimbus. Okay. So based on height, we had three prefixes, which are cirro and onto, and based on shape, we had three types: cirrus, stratus, and cumulus. And if it is a rain-bearing cloud, it will have the prefix of nimbus. Now let's see some examples of clouds. Like based on, so this is how the clouds are generally named. Now let's see some of the examples of clouds. So the first one is high-level clouds, which are found at a height greater than 20,000 feet or greater than 6,000, approximately 6,000 meters. So they are first one, cirrus clouds. So cirro indicated as it is basically a high level cloud. So cirrus, then cirro cumulus, where cirro indicates the height and cumulus indicates the shape. And then third one is cirro stratus. So if you see the prefix of cirro, it basically means it is a high level cloud. Now the second type is the mid-level clouds, which are basically found at a height of between 1,800 meter to 20,000 feet. So mid-level clouds, what is the prefix that we use for mid-level? It is alto, stratus, and alto cumulus. Now the third one is the low-level clouds, which doesn't have a prefix. So the examples of low-level clouds are just stratus, then nimbostratus. Nimbostratus means it is having the shape of a stratus cloud, and it is basically a rain-bearing cloud. That's why the name nimbostratus came. So nimbo basically indicates it as a rain-bearing cloud, or it is capable of producing precipitation. And third one is strato. So these are examples of high level, mid level, and low level. So here we can see when we look at the low level clouds, these are at a height of less than 2000 meter. These are low level clouds. Then at a height between 6500 to 23,000 feet, we have altocumulus and altostratus, and the high clouds are cirrus. So cirrus, we can see these are that. This is basically having that layered or not layered, curly or fibrous structure. This is cirrus, and then cirrostratus is there, which appears like a thin layer of cloud. Thin layer of just appears as thin layer, and then we have cirrocumulus. Cirrocumulus is kind of small lumps. It will appear as small lumps. It is kind of filed up. Then the second one is altocumulus and altostratus. So altocumulus, again we can see it is kind of small lumps we can see in case of cumulus, and altostratus again is just a single layer of cloud. And then in low level clouds we have nimbostratus and stratocumulus. So stratocumulus is cumulus only, but it is kind of extended, or it is kind of layered. And then we have the cumulus, stratocumulus, and stratus we have in case of low level clouds. And there is another type of cloud which is basically known as cumulonimbus. So we classified these clouds based on their height. So now there is another type of clouds which are capable of vertically developing. Now there is a third type, which is the fourth type. This is generally vertically developing. The height of the cloud kind of increases. It extends to a higher height in the atmosphere. As you can see, this is a single cloud. Like it starts from the base of the cloud is around here, and it goes up to a height greater than 7 kilometers. So this is a vertically developing cloud. This much vertical development it has. So this is basically known as cumulonimbus. This kind of vertically developing clouds are known as cumulonimbus. These type of clouds you can generally see associated with the cyclone or storm condition. So that's how these clouds are generally formed. This is cumulonimbus. So if you remember last class we studied about the different levels in the atmosphere, like level of lifting condensation level, level of deconduction, level of neutral buoyancy, and all. So that time I told you generally the base of the cloud is over the level of lifting condensation level. So this is generally LCL, and the level of neutral buoyancy is where the cloud generally stops growing. Like above it, the clouds only exist. So that is level of neutral buoyancy. Because above that, the temperature with respect to height increases in the atmosphere. So it is not possible for the cloud to develop further beyond that. So generally, that is the top of the cloud, which is known as level of neutral buoyancy. And as you can see, since the formation of here stops over here, the cloud is kind of extending. Since it is not able to develop vertically, it is kind of extending horizontally and then forming a shape of an angle. Generally, these thunderstorm clouds or these cumulonimbus clouds have this anvil top. So these are vertically developing. So we have high level clouds. Examples are cirrus, cirrocumulus, and cirrostratus. Then here we have mid level clouds, altostratus and altocumulus. We have low level clouds, which are stratus, we also have vertically developing clouds. Examples are cumulus and cumulo. Some of the cumulus clouds also undergo this vertical development. Cumulus and cumulo. This is an example of cumulonimbus clouds. It is vertically developed. So cumulus and cumulo. So generally these cumulonimbus clouds will be associated with they produce rain showers and light snow. Generally associated with hail. They generally produce rain, light snow or hail, and they generally are associated with thunderstorms, cyclones, etc. Associated with thunder. Now, so that is about clouds, how they are named, what are the different types, classifications based on height. So now we will look at a particular type of cloud, which is fog. Fog, like you will be familiar with the term fog. So what exactly is fog? So fog is actually a cloud only, which is formed very close to the ground. So fog is also a cloud which is generally formed very close to the ground. So fog forms when air saturates, when the air becomes saturated, generally fog forms, which means the relative humidity is 100%. That is very high moisture content in the atmosphere, and the water vapor in the parcel condenses to form water. And the air generally, the saturation is reached either by, how to reach saturation we have learned in the last class. So there are two ways in which saturation can be reached. One is by lowering the temperature of the air parcel. The second one is by adding more moisture to the parcel. So there are two ways in which a parcel can attain saturation. So fog generally forms when air has high level of moisture in it, or it is very close to, or the surface temperature is very much low. So in these conditions, generally fog forms, which is also a cloud which is formed very close to the ground. So now there are different types of fog based on its formation mechanism. So the first one is the radiation. This thing I took from your NPTEL class. So radiation fog generally forms during night time. So basically due to so in the last in the initial classes I have told you that generally the atmosphere is heated by the outgoing long wave radiation. So the source of heat or source of energy to the atmosphere is basically the outgoing long wave radiation, which means the earth absorbs, or the earth gets heated up due to the incoming shortwave solar radiation, and then after attaining a particular temperature it starts re-emitting the energy in the form of long wave radiation. So the atmosphere is generally warmed up due to this outgoing long wave radiation. So during night time, due to the absence of incoming solar radiation, the surface of the earth will be very much cool. So because of this cool surface, so when the temperature lowers, what happens is that the air becomes saturated more easily. Or dew point temperature will be attained. So the actual temperature becomes the dew point temperature. So saturation occurs. water droplets will be found very close to the surface. So it appears as a fog. So during night time, the Earth's surface will be cooler. T reduces and reaches TD, and then it results in the formation of fog. Air parcel will be saturated, it will condense and form water droplets, which is basically fog. So that is radiation fog, which generally forms at the second one is the advection fog. Advection fog means if an air parcel which is moist is moving like this. So here the temperature is T, suppose, and it is moving like this, and it reaches another point. Suppose here the temperature is this T1 and this is T2. Suppose T2 is less than T1. So as the temperature lowers, as the parcel is moving to a colder surface, above a colder surface, if that temperature T2 is equal to the dew point temperature of the parcel, then again the parcel will become saturated and then condensation. So this generally occurs when air parcels moves over a colder surface. So this generally occurs when air moves over a colder surface. So this is advection fog. The horizontally moving air parcel comes in contact with the colder surface. Then, because of the sudden temperature lowering, the parcel will become saturated and eventually condenses. So generally, this occurs in a large, like when the parcel moves over a cold body of water or snow or ice cover, whose temperature is well below the dew point temperature of the advecting air. So that is advection fog. Now the third type is the upslope fog. So in case of upslope fog, what happens is that moisture is flowing through a surface. Due to the elevated terrain, the parcel is forced to move up. So as it goes up, the temperature reduces. So due to forced uplift over a elevated terrain, the temperature is lower, the temperature of the parcels becomes equal to dew point temperature, saturates. That is upslope. Fourth one is valley fog. Valley fog means the cold air over the slope of mountains or terrains is forced to come down due to its higher density. As it will be cold, so since there is a lower surface over here, the parcel is forced to come down to this valley kind of thing from the slopes. So this reduces the temperature, and then so very cold air is coming to the valley. So the temperature is lower, gets saturated and then condenses. So that is valley fog. Valley fog is happening because the cold air from the sides of the mountains come down and deposits in the valley. So that is the fourth type. So there are four types of fog. First one was the radiation fog, which generally forms at night due to the lower surface temperature. Second one was the advection fog, which happens when an air parcel, moist air parcel, moves over a cold surface. Generally happens when the parcel moves over a cold body of water or snow or ice cover, whose temperature is well below the dew point temperature of the adjacent air mass. And then the third one is upslope fog. It forms when the air parcel is forced to um, move in the elevated terrain. So since the temperature is lower over those regions, it will get saturated. And then the second one is the valley fog, which forms when cold dense air settles in the lower parts of the valley. So this generally lasts for several days in calm conditions, generally during winter months. And the upslope fog generally forms when winds take this air to the upslope region. And as it goes up, the temperature reduces and moisture in it continues. So that is valley fog. So we just learned what are the nomenclature of clouds, what are the prefixes used based on the height, and what is the name, second part of the names used based on the shape of the cloud. We also learned about the vertically developing cumulonimbus clouds and the rain-bearing nimbus stratus or nimbus clouds. And we learned about what is fog, which is basically cloud formed very close to the ground. And we also learned different types of fog, which is radiation fog, projection fog, and valley fog or upslope fog, four different types of fog. Now let's move on to the stability of the atmosphere. So we will be mostly discussing about the stability So we will just revise what are the different types of lapse rates we learned in the last class. So the first one is the dry adiabatic lapse rate or DALR. In this case, the air parcel doesn't contain water vapor in it. Second one, and it is given by the equation gamma D is equal to minus 9.8 Kelvin per dry adiabatic. This is the rate at which the temperature reduces for a dry air parcel. The second one is the moist adiabatic lapse rate or MA. In this case, the air parcel as water vapor but it is not. So NALR is given by gamma D into 1 minus 0.9 into R Kelvin per, where R is the mixing ratio of the parcel. So indicate, yeah, when the parcel is moist, the amount of water vapor present in the air parcel also needs to be considered. So there is an additional term to the dry adiabatic lapse rate, which is 1 minus 0.9 into. So sense, the mixing ratio, the value of mixing ratio will always be greater than R in case of a Morse parcel. The value of gamma m is always less than gamma d. So the rate at which the temperature will decrease for a moist air parcel is less than the rate at which the temperature will decrease for a dry air parcel. So which will cool faster? The dry air generally will cool faster compared to the moist parcel. So gamma m is less than gamma d. So generally, since gamma n will approximately equal to gamma d itself, in most of the cases their values will be very close to each other. Now the third one is the saturated adiabatic lapse. Saturated adiabatic lapse rate is given by gamma W. The equation of gamma W is minus G by Cv, which is gamma D, into 1 plus LV by G into VRS by V, where RS is the saturation maximum ratio, RS is the saturation maximum ratio, LV. So once the parcel is saturated, there comes the condensation will start to occur in the parcel. So there will be a release of latent heat. So that's why this additional term LV by G into VRS by dZ is coming. So LV is latent heat of vaporization. LV by G into DRS by dZ minus G by Cp into 1 plus LV by G into DRS by dZ. So generally the gamma D will be having the highest value. Then the moist adiabatic lapse rate will come. Then comes the saturated adiabatic. So in case of saturated adiabatic lapse rate, the rate at which the temperature reduces will be further less compared to the moist adiabatic lapse rate, because in this case there is an additional supply of heat by the condensation that is occurring in the parcel. So the heat that is released during the condensation process will be added to the parcel itself. So even though there will be a decrease with respect to height, this additional supply of energy or additional supply of heat try to compensate for the heat loss. So that is three different types of lapse rate: dry adiabatic lapse rate, moist adiabatic lapse rate, and saturated adiabatic lapse rate. So last class we discussed about what is the base of the cloud, what is the lifting condensation level, etc. So LCL is basically the base of the cloud. So if the environmental lapse rate is going, this is the environmental lapse rate, or the rate at which the temperature reduces for the surrounding of the air parcel. And this is the air parcel that was initially dry, or it had some amount of moisture. It was reducing its temperature at the rate gamma D or gamma m, which is almost equal. And this is LCL. At this point, the parcel became saturated, and once it is saturated, temperature of the parcel starts to rise because of the additional supply of heat by the latent heat of condensation, and after some point it will become that of the surrounding temperature. So which means after LFC, the parcel doesn't need an external agency at the bottom. See, it will rise on its own. So that was LFC. So when we and I also told you, like, LCL is generally considered as the base of the cloud, where the condensation starts. So that is generally the base of the. Now let's estimate the height of the cloud, or base of the cloud from surface. How to estimate the height of the cloud? By height of the cloud, I mean the base of the cloud. From what height the cloud starts from. How to estimate the height of the yeah. How to estimate the height of the cloud? So from Clausius Clayton equation, from the Clausius Clayton equation, we know dEs by dt is equal to minus LV Es by RV into t. This is the Clausius Clayton equation, where LV is the rate limit of vaporization, RV is the specific gas constant for water vapor. It is having a value of around 469 for water vapor. Then ES is the saturation vapor pressure, T is the temperature. So this is a closest electron equation. So when we reach LCL, so at LCL, the parcel becomes saturated, right? So what happens? The temperature of the parcel will become the dew point temperature, and the vapor pressure of the parcel will become the saturation vapor pressure. This is T and this is T1. Now we use 2 in 1. At LCL, the Cauchy electron equation becomes dE by dt, because E and ES are equal, becomes minus LVE by RV. T is the dew point temperature, so PV square, RV into PV square. And when we learned about the basic assumptions of an air parcel, let us assume that the vertical motion, rising or sinking of the air parcel, all vertical motions of the air parcel is considered to be adiabatic. So we already know the parcel is undergoing an adiabatic process. Diabatic expansion, as it is rising high in the atmosphere, basically expands. Diabatic process, which is basically an expansion. Adiabatic expansion. The parcel is undergoing adiabatic expansion. So in that case, the equation of state becomes T raised to minus chi is equal to a constant. This is the equation of state for an adiabatic process, where chi is given by R by C. So T raised to minus gamma minus chi is equal to a constant. Now we take the differential in both sides. T dt is basically if we take the logarithm on both sides, it will become log T is equal to I into log. Now if we take the differential, it will become dt by T is equal to chi into, let's replace pressure with the vapor pressure E, chi into dE by T. Now we write dE by E is equal to 1 by chi into dt by, so now we have an expression for dE by E is equal to 1 by chi into dt, right? So earlier from Cauchy's electron equation, we got dE by dt, or this can be written as dE by E is equal to minus LV by RV d square into dt. So if we both are having the same left hand side d by e. So we can equate hand side of the equation. So from here, this is the equation 3. From the Cauchy-Skelton equation, we got this will be the value of d by e. And then from the equation of state for an adiabatic process, we got d by e into 1 by chi dt by d. Now we equate these two. We will get 1 by chi dt by t is equal to minus LV dTd by RV into dt, or we can write dTd equal to minus RV by chi Td square by LVT into dt. dTd, the change in dew point temperature is equal to minus RV by chi into Td square by LVT into dt. Now we consider the base of the cloud. This is the surface. Suppose this side is equal to 0. Here the surface temperature is T, and the dew point temperature of the surface is Td1. Now this is the height at which the parcel forms, or the cloud forms. Assume that this is the cloud, even though it doesn't look like cloud. And this is the height of lifting condensation level, which is Z is equal to LCL. So here the temperature is Td2, and let the temperature be Tc. Temperature of this particular height be Tc. The temperature at which condensation becomes Tc. Now we want to delta T will be T minus Tc. So the temperature at the surface minus temperature at the base of the cloud. So generally in the atmosphere, this is basically surface or environment. It is generally 10 Kelvin per kilometer. This will be the value. And delta Td, that is the change in the dew point temperature, will be Td2 minus Td1 minus Td. Delta Td can be written as Td1 minus Tc. Tc means at that particular height, or at Z is equal to LCL, Td dew point temperature and the surface temperature, or the environment temperature, both are equal. So Td2 can be written as Tc as well. So delta Td becomes Td1 minus delta Td becomes Td1 minus Tc. This is equation number 4. Another equation, which is basically the relationship between the dew point and temperature T, is given by 1 by 6 into delta, or we can write 1 by 6 into 10 delta. 10 is the change in the temperature. It is basically the collapse rate value, 9.8 Kelvin per kilometer, approximately 10 Kelvin per kilometer. So 1 by 6 into 10 into delta set will be delta Td. we write delta TD minus delta T becomes, so delta TD is basically 10 by 6 into delta Z, right? That's what we got just now. And delta T is 10 delta Z. 10 is the lapse rate of the, so delta Z, 10 delta Z. So here, from here we got delta TD is 1 by 6 into 10 delta Z. From here we got delta T is equal to 10 delta Z. So now if we want to find delta TD minus delta T, we'll get 10 by 6 delta Z minus 10 delta Z. Or it will become, so if we write delta TD, from here we can write TD1 minus TC. Instead of delta TD, we can write TD1 minus TC, and delta T is basically T minus T is equal to 10 delta Z minus 10 delta Z become minus 50 delta Z by 6. TC and TC will be gone. TD1 minus T is equal to minus 50 delta Z by 6, or delta Z becomes 6 by 50 into T minus TD1. If you take out the negative sign, it becomes T minus TD1. Or we can write delta Z is equal to 6 by 50 is basically having a value of around 0.1. So delta Z becomes 0.12 into T minus TD. This is the equation to find delta Z, or the base of the cloud from the surface. From Z is equal to 0, delta Z is the height at which which is basically the height of the cloud. Based on the surface temperature and the dew point temperature at the surface, we can determine TD1 as the dew point temperature of the surface. We can determine the height at which the cloud will be. We can calculate the height of the cloud base. So we started from the Clausius-Liebman equation. Then we got the value for d by e. Then as the second part, we started from the equation of stage 4 in adiabatic process, which is T e raised to minus gamma is equal to constant. From there also we got the value of dE by. Then we got the relationship for dTd minus dTd, delta TD. We got the equation for delta TD. Then we substituted based on the temperature references of the surface and the base of the cloud. Finally, we got the value of delta Z to be 0.12 into T minus TD. Now, suppose we will solve a question. Suppose its surface temperature is having a value of 277 Kelvin and TD is having a value of 273 Kelvin. Can you calculate the value of delta Z, the height at which the cloud will be found? So the equation is delta Z is equal to 0.12 into T minus TD, which is 0.12 into T minus TD is 277 minus 273, just 0.12 into 4. It will be around 0.48. Suppose at the surface, this basically gives the value in terms of kilometer. So suppose at the surface temperature is 277 and the dew point temperature is 273 over a surface, then the height at which the clouds will be formed is basically given by 0.48 or we can write delta z is equal to 480 meter. Another question, T is equal to 30 degrees Celsius, which is 303 Kelvin, and TD is equal to 18 degrees Celsius or 291 Kelvin. And what will be the value of delta Z? Can you calculate and tell me what will be the value? Please calculate and tell me in the second case what will be the value of delta Z. Where the surface temperature is 277 Kelvin and the dew point temperature is 273. It will come around 1.44 kilometer or approximately 1.5. So the value will be approximately 1.44 kilometer or 1.5. So that is the height at which the clouds will. Now, suppose there is an air parcel at some height. This is height, air parcel at maybe z is equal to 7. So by some external force, we raise the air parcel from z is equal to z1 to another height. Let it be z is equal to z2. So if we displace the air parcel, the air parcel from its initial position, there are two possibilities. First one is that the parcel will start moving in the displaced second possibility is that the parcel come back to its initial position. So suppose if we displace an air parcel two possibilities are there. Either the parcel will start moving in the displaced direction or the parcel may come back to its initial position. The first case, when the parcel continues to move in the displaced direction, we say that the atmosphere is unstable. And in the second case, if it comes back to the original position, we say that the parcel is stable. The first one is unstable equilibrium, and the second one is stable equilibrium. Now, when we learned about the basic assumptions of an air parcel, we learned that. So initially, we discussed what are the basic assumptions for an air parcel to be. So, and then one of the assumptions is that the air parcel exists in an environment that is in hydrostatic equilibrium. The air parcel exists in an environment which is in hydrostatic equilibrium. Hydrostatic equilibrium in the sense dp by dz, the equation dp by dz is equal to minus rho g, will be followed by the air parcel. The second one, at any given level, at any given level, the pressure of the parcel and environment are equal. So suppose there is a parcel at a height of 1000 hectopascal. The pressure of the parcel, at we can remove it as P dash, will be equal to 1000 hectopascal. Now suppose if we raise the parcel to a height of 700 hectopascal, the parcel will immediately adjust its pressure so that it will be equal to the surrounding pressure. So at any given level, if we look at the pressure of the parcel, it will be equal to the environment pressure itself. So that is another assumption that we have for the parcel, which means P dash will be equal to P. Suppose let us assume we have an air parcel with density rho dash, pressure P dash, and the surrounding density of the surrounding air is given by density is equal to rho, and the surrounding pressure is so as I said earlier, the environment surrounding the parcel will always be in hydrostatic equilibrium, which means dp by dz will be equal to minus rho g. This is in case of the environment. In case of the parcel, the parcel, suppose the parcel is moving at an acceleration, vertical acceleration of d square set by dt square. Then we can write the vertical acceleration will be equal to the hydrostatic dp by dz plus rho dash g is equal to d square set by dt square. So if the parcel is having a vertical acceleration and dp by dz is equal to minus rho g, or dp by dz plus rho g will not be equal to 0. Instead it will be equating to the acceleration of the parcel. So d square t by dc square, which is basically the vertical acceleration of the parcel, will be equal to d p dash by dz plus rho dash into g minus rho dash into d square. Rho dash is also equal to minus rho dash into d square set by dt square. It is in the form mass into acceleration. The force it is of the form mass into acceleration and into acceleration d square set by dt square. The force will be equal to the dp dash by dz plus rho dash into g. This is in case of parcel. Now we have the equation for hydrostatic equilibrium in case of the environment and in case of. So the parcel is having a vertical acceleration of d square set by dt. At any time, p dash will be equal to p because the pressure of the parcel and pressure of the environment will be equal. So we can write dp dash by dz is equal to dp by dz. So it will reduce to dp dash by dz is equal to dp by dz, and we know dp by dz is equal to minus rho g. dp dash by dz is equal to dp by dz, which is equal to minus rho g. So we substituted here, it will become minus rho g plus rho dash into g is equal to minus rho dash into d square set by dt square. Or we can write d square set dt square is equal to g into, we take g outside, rho dash minus rho both sides. Here. So we substituted, we know dp dash by dz is equal to dp by dz, which is equal to minus rho g. We substitute it in the equation for vertical acceleration case of parcel. That is, we substitute this dp dash by dz by minus rho g. It will become minus rho g plus rho g is equal to minus rho dash into d square set by dt square. Minus rho g plus rho dash into g is equal to d square z by dt square. Now we are writing the equation for d square z by dt square, which is the acceleration. D square z by dt square can be written as, from here if you take g out, it will be g into rho dash minus rho divided by minus rho dash rho. So we can, to eliminate is the equation for d square z by d square z by dt square into g into rho minus rho dash by so now from the ideal gas equation we can write P is equal to rho RT. From the ideal gas equation we can write P is equal to rho RT. We can write rho is equal to P by R. Rho is proportional to 1 by so rho dash rho by rho dash rho by rho dash can be written as so in case of a moisture parcel, so here we are mostly discussing about vertically accelerated moisture parcel. So in that case, T will become TB, which is the virtual temperature we have already discussed. So rho by rho dash will become TB dash by TB, right? From this, since rho is inversely proportional to 1 by TB, rho by rho dash is proportional to 1 by TB dash. If we take rho by rho dash, it will become TB dash by. Now we substitute this in our equation. T square z by dt square becomes. We are consider we are dividing each quantity by rho. We are dividing each quantity by rho dash. So g by so it will become TB dash minus TB by will reduce to d square by d square z by d square is equal to TB dash by TB. This is known as a buoyancy force. Buoyancy d square by d square z by dt square becomes g into TB dash minus TB by TB. The virtual temperature of the parcel TB dash is given by temperature at the surface minus gamma V. This is the moisture adiabatic lapse rate into dc, right? This is the lapse rate for parcel. Gamma is the moisture adiabatic lapse rate. And in case of the environment, we can write TB is equal to TB0 minus gamma V into dc, where gamma V is the environment lapse rate. So the lapse rate of the surface, the lapse rate of the environment. So TB dash can be written as TB0 minus gamma V into dc, and TB, which is the temperature of the environment, can be written as TB0 minus gamma V into dc. Now if we substitute this to the equation that we got for d square z by dt square in terms of temperature, we can write d square z by dt square is equal to just TB dash minus TB, right? So TB dash is basically TB0 dash minus gamma V dash into dz minus TB. TB is TB0 minus gamma into dz divided by TB into G by T, or d square z by dt square is equal to G by TB PV0 dash at the surface, the temperature of the parcel and the temperature of the environment will be same. PV0 dash and PV0 are same. So this and this will cut off. The remaining terms are gamma V minus gamma V dash. The lapse rate of the environment minus the lapse rate of the parcel into dz. So this is the equation for the vertical acceleration in terms of lapse rate. So we found the equation in terms of temperature, in terms of lapse rate, and in terms of the density of the parcel and the environment. Now this equation is basically having the form of d square x by dt square plus omega square x is equal to 0. Where omega in our case is basically g by tv into gamma v minus gamma v dash. In our case, the value of omega is g by tv into gamma v minus gamma v dash. So the solution for these type of equations are already known. It's just given by, so the solution for the differential equation of this form is given by x is equal to a sin omega t plus b cos omega t. So this is the solution for the equation, and omega is positive, which means gamma v is greater than gamma v dash, or the environment lapse rate is greater than the Marsh adiabatic lapse rate. The rate at which the temperature reduces over the environment is greater compared to the temperature at which the parcel is temperature of the parcel is reducing. So if we take up at a particular point, the surface will be at a lower temperature due to the higher lapse rate compared to the temperature of the parcel. It is having a lower lapse rate. So in that case, the solution of the equation becomes x is equal to a sin omega t plus b cos omega t. So this is having this kind of sinusoidal structure. The solution is basically kind of having that, which means the parcel is oscillating with respect to its initial position. So the z is equal to 0, or z is equal to some height. Parcel is like this. If it is displaced like this, it will come back to its original position, then it will again go back, will again come back, go back. It is kind of oscillating with respect to its initial position. So in this case, the parcel is said to be stable. It is not displacing. It is not going farther from the displaced position. It is kind of coming back, then again going up, coming. It is kind of oscillating with respect to its original position. So in that case, the atmosphere is said to be stable. So this is the first case. Now the second case, d square x by dt square minus omega square x is equal to 0. Omega is negative. Omega is negative in the sense g by tv into gamma v minus gamma v dash is less than 0, which means gamma v should be less than gamma v dash, which means the environmental lapse rate is less than the Marsh adiabatic lapse rate. So the rate at which the temperature decreases over the environment is less than the rate at which the temperature decreases for the parcel. So in this case, if we take a particular point, the surrounding or the environment temperature will be higher compared to that of the parcel, because the environment is actually reducing the temperature compared to that of the parcel. So in this case, when omega is negative, the solution for the differential equation of this form, d square x by dt square minus omega square x is equal to 0, is basically e raised to omega t is equal to e raised to omega t. So basically it will have plus or minus omega t. As time goes by, it will be displacing along that path. If it is displaced to a lower height, e raised to minus t if we are considering, it will be like if x is negative, z is negative, it will be like this. So in the first case, gamma v, which is the environmental, is less than, first one was greater than, right? So gamma v is greater than gamma v dash, stable, atmosphere is stable. The parcel will kind of oscillate in its initial position itself. And in case 2, when gamma v was less than gamma v dash, the parcel was unstable. It was moving in the displaced direction, it was not coming back. There is a case 3, which is neutral, in which gamma v equal to gamma v. This is the neutral equilibrium. Now let's see based on temperature. Okay, now we will learn a new term, which is basically known as Brent-Weiss-Taylor frequency. What does that mean by Brent-Weiss-Taylor frequency? So this equation that we got, d square z by dt square is equal to g by tv into omega v minus omega dash into d square, right? Now we told this can be written in the form d square z by dt square is equal to minus omega square z, omega square z. So in this case, omega is basically given g by tv into gamma v minus gamma v dash. It is minus omega, so it will be gamma v dash minus gamma. Hence we are finding the solution for the equation of the form d square z by dt square is equal to minus omega square dz. Here gamma v minus gamma v dash becomes gamma v dash minus gamma v, to compensate for the negatives. Minus omega square. So d square z by dt square minus n square d. It is written in this form generally. So n square is given by g by tv into gamma v dash minus gamma v, or n can be written as root of g by tv is equal into gamma v dash minus gamma v. N square is equal to minus omega square is given by g by tv into gamma G by TV into gamma V dash minus gamma. So this value n is known as a Brunt-Weissala frequency. This basically gives a frequency at which, so since it is square root, this is the equation for Brunt-Weissala frequency. This n is equal to square root of G by TV into gamma V dash minus gamma V. Since it is square root, this is real. It will have a real solution only when gamma V dash is greater than gamma, which means Marsh adiabatic lapse rate is greater than environmental lapse rate, or when in case of stable atmosphere only this will work. It will have a real solution, whereas in case of when it is negative, it will basically have an imaginary solution because the square root will become negative. So n is basically known as the frequency at which the parcel will oscillate about its mean in a stable atmosphere. The frequency at which the parcel will oscillate about its mean position is basically given by the Brunt-Weissala frequency, which is n is equal to G by TV into gamma V dash greater than n. Now let's do a problem related to the Brunt-Weissala frequency. Calculate the Brunt-Weissala frequency n of an air parcel whose virtual temperature PV is 280 Kelvin at P is equal to 750 hectopascal. Assume gamma V is equal to 6 Kelvin per kilometer. So the environmental lapse rate is given. So we have to calculate n for an air parcel whose virtual temperature is 280 Kelvin, pressure is 750 hectopascal. So there is an air parcel with a height of 750 hectopascal from the surface, which is having a virtual temperature, which basically shows how much water content is there in the atmosphere. In the parcel, PV is 280 Kelvin, and gamma V is given as 6 Kelvin per kilometer. We know the rate at which a parcel will reduce its temperature. So gamma V dash, or Marsh adiabatic lapse rate, is approximately equal to gamma D. So we can take the value of gamma D, which is 9.8 Kelvin per kilometer. So from this we know the equation of n is G by TV into gamma V dash minus gamma. Now can you find the value of n? What will be the value of n? What will be the value of n? So if we substitute, it will be root of 9.8 by TV is having a value of 280 Kelvin. So gamma V dash is 9.8 minus gamma V is 6 the root of 9.8 by 280 into 9.8 minus 6 is 3.8. Oh, divided by 1000 will be there because it is in kilometer. 3.8 by 1000. How much it will be? N will be equal to N will be having a value of 0.0115. Try to calculate it and see if it is correct. So this is basically the frequency of oscillation of the pulse. Now I'm not going to derive this, but in terms of potential temperature. So this is in terms of the virtual temperature, right? So the same thing, if we are expressing in terms of potential temperature, it will be Ns equal to root of G by theta V into d theta by dz. Where theta is the potential temperature. So instead of virtual temperature, if we use potential temperature, or if we derive the same thing in terms of potential temperature, we will get the final equation for front Weissler frequency N to be root of G by theta V into d theta by dz, where theta is the potential temperature. Now, just another question in terms of potential temperature of the steam. If the potential temperature of environment theta V is increasing at a rate of 3 Kelvin per kilometer, which means d theta V by dz is equal to 3 Kelvin per, not 3 Kelvin per kilometer, 3 Kelvin per 100 meter. 3 by 100 Kelvin per meter, d theta by dz is given. And theta V, or the potential temperature of the surface, is given by 20 degrees Celsius. V basically shows it as a Marshall air so virtual potential temperature we are considering. So what will be the frequency, what will be the frequency of oscillation of the parcel, frequency of oscillation of the parcel, then so we know that in terms of potential temperature, the equation for the front Weissler frequency is given by Ns equal to root of G by theta V into d theta V by dz. So d theta V by dz is basically 3 by 100 or 0.03 Kelvin per meter. G is having a value of 9.8. Theta V, or the surface potential, virtual potential temperature, is 20 degrees Celsius, which is 3 Kelvin. 0.03. How much it will be? Root of 0.90, root of 9.8 divided by 293 into 0.03. It will be 0.031 second. And such frequency unit is second inverse. Now, if you want to find the time period of oscillation of the parcel, time period of oscillation is given by T is equal to 2 pi by n. This will be 2 into 3.14 by the frequency, which is 0. Around 200 or 198 or 200 seconds it will come. 200 seconds, which is basically 3 point. This is the time period of oscillation of the parcel, and 0.031 second inverse is the frequency of oscillation of the parcel. Okay. So today we learned about what is the different types of clouds, how they are named based on height, based on shape, and some examples of high level clouds, mid level clouds, and low level clouds. Then we looked at what is basically fog, which is nothing but a cloud that is formed very close to the ground. And then we learned 4 different types of fog, which is radiation fog, advection fog, and valley fog, and upslope fog. 4 types we learned. And we learned what is the conditions for a stable atmosphere in terms of um, in terms of lapse rate we learned. So when 3 conditions were learned, in case of the first case was that in which the environmental lapse rate was greater than the moisture adiabatic lapse rate. In that case, it is the parcel is generally stable. The second case, when the environmental lapse rate is less than the moisture adiabatic lapse rate, in that case the parcel is unstable. In the third case, when both are equal, then in that case it will be the atmosphere will be neutral. So we learned 3 types, and then we also learned a new term which is known as a Brunt-Weisser frequency. It basically gives the frequency at which the parcel oscillates with respect to its mean position. And we learned the equation for Brunt-Weisser frequency um, in terms of lapse rate, and also in terms of potential temperature. So if you're solving it from here, it will come in terms of the virtual temperature TV dash minus TV. So we can derive the same conditions like we did for in terms of gamma. Like in the first case, if TV dash is greater than TV, then this term will be positive. When omega is positive, the atmosphere is said to be, what was the condition? When omega is positive, the atmosphere is stable, which means the parcel TV dash minus TV by TV. parcel is having a higher temperature compared to the surroundings, the atmosphere will be unstable, whereas TV dash is less than TV, it will be stable. So the parcel doesn't have the tendency to rise up in the atmosphere, instead it will stay in its initial position. So the parcel temperature is greater than the surrounding temperature, the parcel will rise, whereas when the parcel temperature, which is TV dash, is less than the surrounding temperature, then it will remain in its initial position. So that is in terms of virtual temperature. And in terms of latch rate, we already saw. And in terms of potential temperature also, we learned the equation. I think that is enough for today. We will wind up over here. We will wind up with this. Okay. We'll meet you in the next class. Okay. Thank you. Happy Holi.